Hi, boys and girls, and welcome to another episode of Stupendous Summer Science with Miss Kathy. And today we are going to read The Bot That Scott Built. Let's see about this bot. When we open up, we see lots of gadgets and things that you might use to build a bot. This is written by Kim Norman, illustrated by Agnese Baruzzi. Science Day. This is the bot, the Bippity Bot, the rabbit-eared robot that Scott built. This is the class, the curious class, that gawked at the bot that Scott built. This is the teacher, the talkative teacher, who calmed the class that gawked at the bot that Scott built. These are the ants, the angry ants, that tread on the teacher in polka dot pants, who calmed the class that gawked at the bot that Scott built. Uh-oh, all the ants are coming out of the ant farm. These are the plants, carnivorous plants, that feasted on flies and fiery ants, that tread on the teacher in polka dot pants, who calmed the class that gawked at the bot that Scott built. Carnivorous plants means they eat living creatures like bugs. They don't eat people, but they do eat bugs. This is the frog, the freaky frog that leaped from a log in a bathtub bog to gobble the goodies that piled on plants, that feasted on flies and fiery ants, that tread on the teacher in polka dot pants, who calmed the class that gawked at the bot that Scott built. This is the boa, escaped from its cage, that draped like a microphone cord from the stage, a big-bellied boa that frightened the frog, the freaky frog from the bathtub bog, that gobbled the goodies that piled on plants, that feasted on flies and fiery ants, that tread on the teacher in polka dot pants, who calmed the class that gawked at the bot that Scott built. That bot seems to be the least of their concerns right now. Here's the volcano, the very volcano that bathed the boa in vinegar lava, the big-bellied boa that frightened the frog, the freaky frog from the bathtub bog, that gobbled the goodies that piled on plants, that feasted on flies and fiery ants, that tread on the teacher in polka dot pants, who calmed the class that gawked at the bot that Scott built. This is the spark, the sputtering spark, that sped overhead in an awesome arc, a spark that spit from a Tesla coil, that caused the volcano to bubble and boil. Wait! I know just what to do! Pressing a button called Tesla Coil De-Zapper. Also, Supersonic Serpent Straightener, Volcano Stabilizer, Super Turbo Reptile, and Insect Catcher. There the bot has the snake under control. And there the bot is putting out the flames from the robot. This is the hero, the handy hero, who managed the mess from the very volcano that bathed the boa in vinegar lava, the big-bellied boa that frightened the frog, the freaky frog from the bathtub bog, that gobbled the goodies that piled on plants, that feasted on flies and fiery ants, that tread on the teacher in polka dot pants, who called for the class to cheer for the bot that Scott built. High five, Bippity. Pop, pop, pop. Yay, Scott the bot. Woohoo, Bippity bot. Woohoo, everyone's cheering, and in the cheering, the frog gets let loose, lands on the teacher, and there's something splashing in the bathtub. Oops, and somebody falling into the bathtub. Whoopsie. But Scott's robot saved the day with that big python and all those ants loose and frogs and volcanoes. Oh my, that was a bunch of science experiments gone awry. And that was the bot that Scott built. Stay tuned for more science fun with Miss Kathy. Hi, boys and girls, and welcome to another episode of Stupendous Summer Science with Miss Kathy. Today we are going to do a couple balloon experiments, and the first one is a self-inflating balloon, one that you don't have to blow up yourself. So I have a test tube here with half filled with some vinegar, and that is standing up there. And now we are going to give this balloon, I've been stretching it, we're going to use this funnel here to put some baking soda inside the balloon. So let's pour some of the baking soda into the balloon here. Have to make sure that it's broken up fine enough to fall down into the balloon. Sometimes it gets stuck in the narrow passageway there. Like this appears to be. It's not shaking down anymore. But there's a good bit in there. I think we have enough. Okay. Then we're going to shake the balloon. All the baking soda should be at the bottom. And then once we are done that, we are going to stretch the opening of the balloon until it's over the opening of the test tube. So hopefully this will stretch this far. Do you want to come a little bit closer so you can see? And we're going to stretch this over. It's got to be a nice tight fit. And then once it's attached, we are going to lift the rest of the balloon so the baking soda falls into the vinegar. And then we're going to watch and see what happens. I'm holding this down so it doesn't escape. Look at that go. Our balloon is filling up all by itself. Ta-da! Didn't get real big, but it did inflate. We probably had a bigger inflation if we had more baking soda in it. What's happening here is the vinegar is an acid, and it's creating a chemical reaction with the baking soda that is the base. When the two substances mix, you get carbonic acid, which is unstable and falls apart to become carbon dioxide. That's the gas that's filling up the balloon. And water. Since the carbon dioxide is much less dense or solid than the stuff you use to create it, It wants to expand, and the balloon is stretchy enough to let it do just that. So, voila. We just have to tie it up, and we can hang it up for our party, if we wanted to have a party. So stay tuned for more balloon science with Miss Kathy. Okay, let's try another experiment here with static electricity. I have charged this balloon and I have a piece of thread hanging off my finger. I'm going to put this balloon up against the bottom of the piece of thread, and let's see what it will do to the piece of thread. It's kind of hard to see this thin little white thread I have hanging off my pinky here, but hopefully we will get it to do something once we pick it back up again here. So holding the electricity, the charged balloon. We've only got the electricity to work once so far today, and that was the one that we did not film. So we are not doing so good here. The thread is kind of clinging to the balloon. You can see that. I thought, there we go. We're supposed to be able to slowly make the thread rise into the air. So there we have, and there it is trying to get away from the charged surface of the balloon, moving kind of on its own. Even though there is no wind here, it's just the static electricity making it move. And probably most of that has worn off by now, so it's not going to do any more rising. But that was a little bit of rising to see the thread being moved by the balloon without touching each other. Oh, there we go. That's a little bit better. Of course, part of that's the breeze going on here too, so the breeze don't help, doesn't that hurt? Stay tuned for more stupendous summer science. Hi, boys and girls. Miss Kathy here with another episode, or another piece of an episode of Stupendous Summer Science, and we are holding a pop can over a flame on the stove. There is 1 tablespoon of cold water in the pop can, and sitting next to it is a bowl of ice water. No, we are not going to melt the can, but we are going to try to crush the can without using any of our own force. So we are heating this above the flame for about 45 seconds or so. It may take a little longer. You should start seeing steam come out the top of the bottle, and you should be able to hear the water inside kind of bubbling away. So it may take longer than 45 seconds. You want to use tongs that are metal so that you're not melting plastic tongs, holding them above the flames like this. Sounds like something is happening with that water inside. I'm not seeing steam yet. But we are heating it up. And at least a little bit of residue water that was on the rim of the can is bubbling.
Steam.
Okay, there is steam coming out now, so now I'm going to quickly take this bottle and turn it into this bottle of very cold ice water we have there, making sure the top of the can is immersed fully in the water, and then we will see what happens to our can, if this is going to work or not. So let's give it a go here on the count of 3. 1, 2, 3. Well, I think the problem was I wasn't holding the can. Let's try it again. It did a little bit of collapsing, but I lost my grip on the can. You have to make sure you hold it under that. So our can is not very badly dented, so let's try it again with the water that is in there right now. I think I have to hold it down at the base a little bit more, and then it will be easier to keep it in the cold water. There is still water in the can. Sometimes when you try an experiment, it doesn't work. We keep saying this because we keep having failures. And you have to try again. So now I know I'm going to hold it a little bit farther down the base of the can so that it's easier to get down inside the bowl. Maybe if I had a full bowl full of water, that might help. If I add some more water to the bowl to make sure that it is easy to dunk the can in. Maybe that would be better. Can you give me that pink picture that's standing over there, assistant, please? And we will even add more water. Making sure that it is easy to get this can inserted into the water. Okay, let's see what's going to happen here. I hear things happening inside. Let's see if we're going to get steam is coming out. So let's try it one more time on the count of 3. 1, 2, 3. And there you go. You have a crushed can with a dramatic pop. Okay, let's find out why that happened. Let's see, make sure this isn't too hot to touch. And there is our can just by dunking it in the cold water. Water is liquid at room temperature and room pressure, but transforms to water vapor when it's heated and boils, as we know. Water vapor or steam takes up more space than liquid water, so some of the air inside the can is pushed out the top. When the can is dunked in the cold water, that water vapor condenses and returns back to its liquid state, which takes up less volume in the can. There is now less air in the can, and because the opening of the can is sealed under the water, it is unable to flow in and fill it back up again. This makes the air pressure inside the can lower than the air pressure outside the can. A higher air pressure outside exerts a force on the can. If the pressure difference is big enough, the force is strong enough to crush the can. Dun, 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 dun. Okay. That is an experiment you can do at home with adult supervision because you are using the stove and heating that up. You can do things further. Do you think the can will still crush if you do not pour water into the can before heating it? What happens if you chill the cold water further by adding ice cubes? Well, we did that because we didn't have very cold water. Does the size and shape of the can affect how much it crushes? So if we wanted to, we could try another experiment right now, not pouring water into the can before heating it. Let's see what will happen if we do that. I'm going to go grab one more can. And we will see. We're not going to put any water in this can. We're going to get this old can out of there. And see if we heat up this can. Of course, I'm not sure how, if it doesn't have any water in it, how we're going to know that it is heated up enough. We're not going to see steam coming out, so maybe we'll just set our timer for 2 minutes, because it took over a minute with the steam. Let's see how it does without the water inside and without the signs of steam. Now, what do we think is going to happen? Well, we had to do, the whole experiment had to do with the pressure, oops, I'm getting my book wet here. The pressure that built up when the can is dunked in the cold water, the water vapor condensed and returned back to its liquid state, taking up less volume in the can. So now we don't have anything in the can that is making that happen. So my gut instinct says it's probably, oh, look at that. Something inside the can is happening because there is still steam coming out of the can, even though this can has not had liquid in it for probably 2 weeks. I've had it drying out. But we will keep it steaming over here a little bit longer to see if that makes any difference. And then we will see if we can get the pop crush that we had before. Pop, not referring to the can, but to the noise that it makes. Well, now the whole thing looks like it's about to start on fire. So maybe we will do on the count of 3. 1, 2, 3. Yeah, that one didn't have the same effect, did it? Because it doesn't have the water inside. The can itself was heating up, but without that water pressure inside, we found that it does not work quite the same. So, again, something you can try at home with adult supervision. Thanks for watching today, and stay tuned for more stupendous summer science with Miss Kathy. There's my cue.